Hi everyone. Today we are going to discuss neural networks. Artificial neural networks have been inspired from biological neural systems. They are one of the most popular class of machine learning methods and are an important component of the state-of-the-art artificial intelligence applications such as voice recognition, weather forecasting, and self-driving cars. The building block of a biological nervous system is a neuron, and likewise, the building block of an artificial neural network is an artificial neuron, also known as a perceptron. An artificial neuron takes its inputs through its dendrites, integrates them, and produces a single output. Each input X has a connection strength or weight associated with it. The contribution of each input X is obtained by multiplying it with its weight. I am going to use the letter Z to represent the summation of the inputs multiplied by their weights. And I will call this summation the total input signal coming into the neuron. There is a special type of input which always has a value of exactly 1. If all the other inputs are 0, this special input provides a baseline input value. This input is sometimes also called the bias term. In some of the slides, I may not show the bias term, but you should know that it is still there. We can rewrite this summation as a series. One way to handle the bias term is to just pretend it is one of the inputs. Let's call it x0 so we can simplify our formula for the total input signal. And if we consider the set of inputs and the set of weights as vectors, we can write the summation as a dot product between x and w vectors. The total input signal in a neuron is processed by an activation function to produce the neuron's output signal. The activation function is a function of the total input z, but you can also write it as a function of the inputs x and the weights w. The activation function we use in a neuron depends on the application. The two most commonly used activation functions are the linear and the sigmoid functions. The linear function simply outputs the total input signal unchanged. The sigmoid function produces an output that is between 0 and 1. The sigmoid function is also known as the logistic function. When I draw a neuron, I will show the shape of the activation function inside the neuron because that's an important property of the neuron. The best thing about a neuron is that we can train it on a training data set that contains a set of samples and their target values, and have the neuron learn to produce the desired outputs for each sample. I will show the dataset as a matrix where each row represents a sample and each column represents a feature or an attribute. This dataset contains N samples and D features. We feed the samples into the neuron one sample at a time. Each feature of a sample becomes one of the input signals going into the neuron. The process of learning involves adjusting the weights of the input signals so that the neuron's output matches the desired target values. I will demonstrate the learning process with a simple example. I will train a neuron that has a linear activation function. I will also simplify the training dataset so it only contains a single sample. And I will simplify the problem even further and assume that we have a single attribute in the dataset, including the bias term that makes two input features. So this linear neuron will have two weights that we can adjust. Let's see what the neuron outputs for this sample. I will feed in the sample into the neuron, calculate the total input signal, and the result of the activation function. We'll have to start off with some random values for the weights. Let's use 5 and 7. Multiplying each input with its weight and adding them up gives us a total of 21.1. The linear activation function produces 21.1 as output. Our desired target value is 2.7, so we have to make changes to the weights so that they produce a value that is closer to 2.7. But how do we do that? We need to define an error measure that captures how far off we are from the desired target value. You might be tempted to just subtract the neuron output and the desired target and use that as the error value. But then you would have to take the absolute value to account for being above or below the target. Using the absolute value does not give us a mathematically clean measure. As you will see, being able to take the derivative of the error measure is important, but taking the derivative of the absolute value is mathematically a little messy. So we are not going to use the absolute error. Instead, we are going to use the most common error metric, which is the difference between output and the target squared. For convenience, we'll multiply that by 1/2 so that when we do take the derivative, we don't have to keep writing the number 2. The current error of our neuron is 169. Changing the weights will change the output, which in turn will change the error. There are many optimization strategies that can be used to adjust the weights to minimize the error. We'll use our favorite method, gradient descent. We have 2 weights to adjust. We would apply gradient descent to both of them. We would change each weight such that we move in the opposite direction of the gradient of the error with respect to that weight. The gradient is multiplied by a learning rate eta to control the magnitude of the adjustment we make. The output y of the linear neuron is equal to W0 times x0 plus W1 times x1. When we plug that into the error formula, we get this. We can then obtain the derivative of the error with respect to W0 and get this. And also with respect to W1 to get this formula. We would then plug each of these to the gradient descent formula to calculate the change we need to make to each weight. We have identified everything we need to update the weights. Let's use a learning rate of 0.1. W0 was 5, and changing it by this much gives us an adjusted value of 3.16. W1 was 7, adjusting it by this much gives us the new W1, 2.77. We update the neuron with these weights. We are now ready to see how these new weights will perform in terms of the error of the output they produce. When we feed the sample data into the neuron again, using these weights now, we get 9.53 as the output, which is closer to the target value 2.7 than before. The error has gone down to 23.3, but we are still not satisfied with the amount of error. We repeat the weight update again, change the weights, feed the sample again, and get the new output. The new error is now 3.2. We repeat the weight update one more time and achieve an error of 0.44. And after we repeat this 10 times, we get an output that's very close to 2.7 and a really small error. We stop the learning process here because we like the results. We have formulated a learning process by which we can adjust the weights so the network produces an output that is close to the desired target. What if we had more attributes in the data? Let's go back to our formulation and come up with a more general weight update rule for each weight. The gradient descent for each of the ith weights is calculated from the partial derivative of the error with respect to that weight. To calculate the partial derivative, we can apply the chain rule to get this. Because we are using a linear activation function, the output y is just equal to the total input z. The derivative of y with respect to z is just 1. And remember that the total input z is just a summation of the weights multiplied by the inputs. The partial derivative of the total signal with respect to any of the ith weights is just xi. For example, the partial derivative of z with respect to w2 is just x2. All of these other terms would become 0 in the derivative. When we plug this back into the derivative of the error, we get this. And plugging that back into the weight update rule gives us this. So if we have any number of inputs in the neuron, we can just apply this weight update rule for each of the weights. What if the neuron had a different activation function? When we had a linear activation, we were able to drop dy dz because y was just equal to z. But now we'll have to keep that. For an arbitrary activation function, the partial derivative of the error will now include the derivative of the activation function. Let's take a look at the case where the sigmoid function is used for activation. The derivative of the sigmoid function is shown here. With a little bit of magic, we can rewrite the derivative as the output y multiplied by 1 minus y. This means that after we feed a sample into the neuron and find the value of y, the derivative of the activation function can simply be written as y times 1 minus y, which is more convenient than having to type or calculate this formula. The partial derivative of the error for a sigmoid function becomes this formula right here. If you had a different activation function, you would have to stick with this general formula, but for sigmoid, we can use this. Let's go back to our training example and use a sigmoid neuron instead of a linear neuron and see how the weights are updated. When we feed the sample into the neuron, calculate the total input signal, and apply the sigmoid function, we get an output value that is just under 1. The error in our output is around 1.4. The derivative of the sigmoid for that total input signal is in the order of 10 to the negative 10, which is a very small number. As a result, the weight update barely makes any change in the weights. When we use these slightly modified weights and feed them into the neuron again, the new output is only slightly different and the error is reduced only slightly. The change is so small that the number of digits I am showing here does not really reflect any change. It turns out that no matter how many times we apply the gradient descent, we cannot get an error less than 1.4. Here you see the result after 1000 iterations, where we were able to make only a tiny difference in the error. There are two problems here. One problem is that the output of the sigmoid function will never go above 1. No matter how we change the weights, we cannot make the output y greater than 1. The other problem is that the derivative of the sigmoid is too small and the weights don't change much. To understand this better, let's examine the properties of the sigmoid function. The total input signal can be any number between negative infinity to positive infinity. The sigmoid function is a saturating function which outputs a value between 0 and 1. Sigmoid function is incapable of producing an output outside of the 0 to 1 range. Because of this saturating behavior, the sigmoid function is not appropriate for learning arbitrary target values. It is only good for learning target values that are between 0 and 1. Another issue with the sigmoid function is that its derivative is too small when the magnitude of the total input signal is too large. Since the weight update in the gradient descent is proportional to the derivative of the activation function, this results in very small weight update values, and that makes the weights change too slowly, requiring many iterations for convergence. This slow behavior also suggests a guideline for how we initialize the weights at the beginning of the training. We have to make sure that those initial random weights are small so that the total input signal remains small where the gradient is at a considerable level. The desired features of an activation function are being continuous, easily differentiable, and monotonic. These properties make gradient descent possible and allow the training to converge. Here are some of the activation functions you may encounter. The hyperbolic tangent function is just a scale version of the sigmoid function. You may come across the step function when you read about activation functions, but it is never really used in practice because it is not differentiable and its derivative is zero, which means the weights would never change if we apply the gradient descent algorithm. Rectified linear unit function is zero for negative values and linear above zero. ReLU function is also non-differentiable at zero, but it has a nice feature that in a network of neurons, it allows some neurons to be inactive. There's a smooth version of the ReLU function that is differentiable. The Gaussian activation function has the property that it turns on for some samples that are close to its mean and stays off for others. Among these activation functions, linear and sigmoid functions are the most commonly used ones. Linear activation function is useful for regression problems where we try to make the neuron learn unbounded and continuous values. That being said, it is still possible to use a linear function for classification by using a threshold on its output. Sigmoid activation function is more appropriate for classification problems where the target value is usually binary. 0 would represent one class and 1 would represent the other. Sigmoid neuron will output a real value between 0 and 1. We would then interpret that output using a threshold of 0.5 to determine whether the neuron thinks the sample is in one class or the other. We discussed training a neuron for just a single sample. How do we make the neuron learn from all the samples in the dataset? The overall error on all the input samples is usually defined as the average of the squared errors from each sample. This is just to get a sense of how the neuron is performing for all the samples. When we are updating the weights, we would need to calculate the gradient for each sample separately. To update the weights for a set of samples, the most commonly used approach is batch learning, where we feed all the patterns to the neuron, calculate the weight update for each sample, but we don't modify the weights until all the samples are processed. We then take the average of the weight updates and modify the neuron's weights with these averages. A single iteration of the batch learning process where we present all the samples is called an epoch. Batch update has the advantage of minimizing the overall error across all the samples at each epoch. Sometimes, because of the nature or the size of the data, it may not be possible to use batch learning. For example, we may be dealing with an application where we constantly get new data samples, such as streaming data obtained from sensors. Or the dataset may just be too large to fit in the computer's memory, making batch learning computationally infeasible. In such cases, we can train the neuron one sample at a time and update the weights after we present each sample. A combination of batch and iterative learning is also possible, where we can feed a subset of the samples to the neuron, update its weights, and then move on to the next subset. A third option is stochastic learning, which is similar to iterative learning, except samples are now picked randomly. In iterative learning, we just use the samples in the order they appear in the dataset. Iterative and stochastic learning tend to be less consistent than batch learning, because when a neuron is trained on each new sample, it may forget about the previous samples. Each new sample kind of pulls the weights toward itself, and the weights end up moving all over the place. To get more consistent learning, we usually run through the dataset multiple times. Our lecture title is Artificial Neural Networks, but all we have done so far is discuss a single neuron. A single neuron is clean and simple, and gradient descent algorithm does a good job of learning the weights from the data. The problem with a single neuron is that it is not powerful enough to learn complex relationships. In fact, if we consider the classification problems, a single neuron is capable of learning only linearly separable datasets. Two classes of samples are linearly separable if and only if there exists a line that separates the samples of one class from the samples of the other class. A linearly non-separable classification problem is where it is not possible to separate the samples of the two classes by a line. It does not matter if you use a linear activation function or a sigmoid function, which is nonlinear. The limitation really comes from the way the total input signal is calculated as a linear function of the sample features. A neural network is where we set up a network of neurons where the output of some of the neurons feed as inputs into other neurons. Let's see if a network of linear neurons is more powerful than a single neuron. I have two neurons here where each of them receive the inputs. I then feed the outputs from these intermediate neurons into a third output neuron. The output from this last neuron is considered to be the output from the entire network. These intermediate neurons are called the hidden neurons. This type of network is called a feed-forward network because the information flows in one direction. I'm using the letters I and J here to distinguish between the hidden neurons and the output neuron. I'm also using the subscript numbers to indicate the source and the target of that connection. For example, this weight right here goes from the first input into the second hidden neuron. If you work out the overall output of the network, you can rewrite it in this form. So the overall output of the network is simply a linear combination of the inputs. We could have easily created a single neuron with those appropriate weights to produce the same output. This was kind of disappointing. Combining multiple linear neurons does not really allow any kind of power in representing more complex formulas than a single neuron could. And it doesn't matter how many neurons you have or how many layers you use. We can show that for any number of linear neurons, you can produce the same output with exactly one single neuron. In other words, if you take linear transformations of input signals from multiple neurons and then linearly combine them again, the overall result is still a linear transformation of the inputs. Using a network of linear neurons does not represent any function that a single neuron cannot. But the same is not true for a network of nonlinear neurons. In fact, a feed-forward network of nonlinear neurons is so powerful, the universal approximation theorem states that it is capable of approximating any continuous function. You of course need to have a sufficient number of neurons in each layer of the network. The universal approximation theorem doesn't really say how we can actually train the network and set the weights. It just says that if we can set the correct weights, the network is capable of approximating any function. From a classification point of view, you can think of each neuron dividing the space, and the neurons in the subsequent layers divide the space further, forming complex decision boundaries. We can certainly increase the number of intermediate layers, and that is something deep learning methods use. Using only one hidden layer and one output layer is one of the most commonly used architectures. A network with only one hidden layer is called a three-layer feed-forward network. The term three-layer is actually a little misleading. Only the hidden and the output layers have neurons in them. The input layer just represents the input values of a sample. Earlier, we showed how a single neuron can be trained using gradient descent. Let's now see how a feed-forward network can be trained. Just like in the single neuron case, we start off by feeding a new sample into the network and calculating the total input signals for each of the hidden neurons. And then the activations from the hidden units are fed into the output neuron to get the final output from the network. We compare the output Y of the network with the desired target value in the sample to calculate the error. Now we need to come up with an error gradient for each of the connections in the network so that we can update the weights using gradient descent. Training the neuron in the output layer is easy. It is just like training a single neuron. I have here the derivative of the error for a single neuron that we derived earlier. In the single neuron, we use the input into that neuron. For the output neuron in a network, the input into it is Yj, which is the output that is coming from the jth hidden unit. I am using Yj and Wj to represent any of these connections. Their weights will be updated following this rule. Let's take a look at the derivative of the error for the hidden unit weights. The influence of the hidden weights on the final output is indirect. We use a method called error backpropagation, which is just a fancy word for applying the chain rule in calculus. To find the derivative of the total signal Zk in the output neuron with respect to Wi in the hidden neuron, we make use of the intermediate variables that link them together. In this case, Yj and Zj provide a connection from Wi to Zk. So we'll rewrite the derivative using the chain rule as the derivative of Zk with Yj multiplied by the derivative of Yj with Zj and multiplied by the derivative of Zj with Wi. Zk is the total input signal of the output neuron, which is equal to the sum of Yj's multiplied by Wj's. So the derivative of Zk with Yj is just the weight Wj. The derivative of Yj with Zj is just the derivative of the activation function for the hidden neuron. Zj is the total activation of the hidden unit, which is just a multiplication of all of its inputs with their respective weights. The derivative of each term in that summation is 0, except for the one containing xi times wi, whose derivative is xi. Let's clean up the formulas a bit. Let's call this part as delta k, so we can reuse it in the hidden neurons too. Similarly, let's call this part in the hidden neuron as delta j. If we had multiple neurons in the output layer, which would happen if we were trying to teach the network more than one target attribute, we would need to incorporate the errors in all of the outputs when we are updating the hidden unit weights. And the way to do that is by summing up the delta k's of all of the output units, weighted by the connections going from the jth hidden neuron into the kth output neuron. This is in a way how we attribute the blame that the jth hidden neuron has in the errors observed in all of the output neurons. This derivative formulation can be extended to work for any feed-forward network with one or more hidden layers. We call this the generalized delta rule. We calculate the delta value of each of the hidden layers by summing up the weighted deltas of the next layer. When you are using a neural network for a machine learning application, you wouldn't really implement the weight update rules yourself. Implementations of gradient descent for feed-forward networks are already available as programming libraries or as separate software tools. In a 3-layer feed-forward network, the number of input and output neurons will depend on how many input and output attributes you have in your dataset. The number of hidden units is something you can adjust. There's no hard rule for how many hidden units you should use, and you should try out different numbers of hidden units to see which one gives you the best performance. The activation functions for the output units will depend on your application. If you are doing regression and predicting unbounded continuous target values, you should use linear activation functions in the output neurons. If you are doing classification where the target values are binary, 0 or 1, you should use a sigmoid function in the output neurons. When programming, you usually need to make use of separate functions for regression or classification networks, or you need to specify which one you want to use as a parameter when setting up your network. Regardless of whether you are doing classification or regression, the hidden unit activation functions should always be nonlinear, and they are usually sigmoid functions. Let's now review some issues with neural networks. A disadvantage of neural networks is that the calculations that are captured in the hidden layers are not easy to interpret. For that reason, neural networks are considered as black boxes that work well in replicating the desired target values, but they do not provide much insight into how they accomplish that. Using gradient descent for weight updates means the neural network training has the limitations of the gradient descent algorithm. The network is typically slow to train, especially if we have a large network with many neurons and a large number of connections. The weights can get stuck in local minima and not improve the error beyond that. To overcome these limitations, we can apply the strategies that we discussed in gradient descent, such as using adaptive learning rate, momentum, and random restarts. A related problem that we have to watch out for is overfitting. Overfitting is when the network becomes very good at replicating the targets for the samples we train it on, but performs poorly for the samples that it has not yet seen. To avoid overfitting, we can use a validation set in order to simulate the neural network's performance on unseen samples. Given a data set, we would set aside a small subset as the validation set. We would train the network and update the weights based only on the error of the training set. As we train the network, we would also keep an eye on the error it produces for the validation set. During the first phase of the training, we would usually see an improvement in the errors for both the training and the validation sets. This is where the network is learning the essence of the samples. After a certain number of iterations, the network would start overfitting to the training set, and the error on the training set will keep decreasing as we update the weights over each epoch. However, the error on the validation set, which acts as an independent performance measure, would start increasing. This is where the network goes beyond the essence of the problem and starts memorizing the samples in the training set. After we complete training, we would go back and identify the epoch where the network had the best validation error and use the weights it had then as our final trained network. The performance on the validation set can also be used to stop the training earlier, so we don't have to keep training the network if it is no longer reducing the validation error. A similar approach can be used to control the number of hidden units used in the network. The overfitting problem happens when the network is too smart and it can memorize the samples. Using fewer number of hidden units reduces the capacity of the network and makes it more likely to learn the essence of the samples and less likely to memorize individual samples. However, we do not want to use too few hidden units that the network is no longer able to learn the desired target values. We can again use a validation set to monitor the network's ability to learn rather than memorize. We can try networks with different numbers of hidden units and use the one that gives the best validation performance. I want to point out that using a validation set is not a substitute for a test set and cross-validation, which I talk about in a separate lecture. Even though the validation set is not used for updating the weights, it is used to make decisions about training, and therefore we are technically making use of those validation samples for training. You still need to check the performance of the network on a separate, independent test set in order to convince people that your network is able to generalize beyond the samples used in training and validation sets. I would like to mention some of the more advanced forms of neural networks before I finish this lecture. Deep learning has been quite popular in recent years, especially in image processing applications such as facial recognition. Deep learning is essentially a neural network with many hidden layers. Because of the huge number of weight parameters that need to be identified, deep networks only work if you have a large amount of data to learn from. The layers of a deep network are organized such that lower layers learn local features from the data, such as edges or colors in an image, whereas higher layers learn more abstract features. An auto-encoder network is where a network is trained to reproduce the input samples, so the target values and the input values are the same. Using a hidden layer with a few number of hidden units, the network is forced to learn a compressed representation of the samples. Auto-encoding networks are used in noise removal and dimension reduction. Sometimes auto-encoders are also used as a first phase in training for a prediction problem. After an auto-encoder is trained, its decompression layer is removed and replaced with output neurons for a different prediction problem. For example, an auto-encoder that has been trained to compress animal pictures can then be repurposed to make a prediction about whether a picture is of a dog or a cat. In training for this new problem, we would lock the auto-encoder weights from changing and only adjust the new neuron weights. This strategy of taking a network that was trained for one dataset and repurposing it for a different problem is called transfer learning. Transfer learning is usually used when we don't have enough samples in our dataset, so we make use of a network that has been trained on a related dataset. To conclude this lecture, I would like to say that neural networks have really survived the test of time and are here to stay. There are many different neural network architectures that are designed for different applications, and we have barely scratched the surface.